So hi, I'm John Kelner, and this is a very long titled talk about how to solve max flow and some of its generalizations in almost linear time. And so the talk I'm going to give today is going to be about joint work with three, well, people, if you don't know them, you will soon. They're all exceptional. So with Lorenzo Orecchia, who's a postdoc at MIT, and Yin Tat Lee and Aaron Sidford, who are grad students at MIT. And they're all great. I should sort of add that and stress that. OK, so today the overview of what I'm going to do is I'm going to focus mainly on max flow, but kind of at a higher level, I'm going to talk about a new general approach for a bunch of the sort of basic kind of fundamental problems in algorithmic graph theory. And in general, I guess this works for ones I'll talk about will be max flow, min ST cut, multi-commodity, and maximum concurrent flow. And I'll define these shortly if you don't remember. More broadly, I'm going to give an approach that lets you break a bunch of very long open running time barriers for solving these problems approximately. But kind of, I guess, more generally, I think there's a nice methodology that's emerging, and I'm going to try to give a general sense of what this methodology is. And today, I'm really going to focus on max flow, and then I'll very briefly just talk about how to generalize it to the other problems. OK, so for the rest of the talk, when I say graph, I mean undirected graph. And I just want to say that in advance. And some of the things that I'm going to brush under the rug are just for convenience. This is not one of those things. Right? This one really, what we're doing, I don't know how to make it work for directed graphs. So this is an actual problem that I don't know how to solve, not just a thing that's going to save me notation. Oh, by the way, before I forget, I'm going to possibly on the sort of background stuff kind of accelerate until somebody stops me. So stop me if I'm accelerating too much. And yeah. OK, good. That was a good example. OK, good. So I guess for the very brief background, and I'm really not going to do justice to the background on this because it's kind of a very well-studied problem. Briefly, that's one of the sort of basic problems in optimization. It's one of the ones that motivated a lot of the historical advances in it. And more importantly, it seems to capture certain core issues in algorithmic graph theory. So it seems that if you look at a lot of other algorithmic questions, speeding up max flow leads to better algorithms for a whole bunch of other things. And the running time barriers that it presents seem to sort of, in order to improve them, you have to actually figure something out. And they seem to capture certain intrinsic challenges. They've also shown up a lot both in the theory and the practice, and they of algorithms, and they kind of motivated a lot of the development of combinatorial optimization. And they are subroutine all over the place. So I'm going to keep that as my background, just because I think people here would probably be a little bit bored if I said too much more, but I'm happy to give the longer description. OK, so let me tell you what the problem is. And today I'm going to talk about max flow, and not really about multi-commodity flow, just to keep things simple. But actually, the framework that I'm going to describe will, with almost no modification, go through for the general case. So OK, the setup is I will have a graph G, which I'll, just to fix the notation, I'll call that VE. It's going to have n vertices and m edges throughout the talk. So whenever I say n, I mean number of vertices, and m is number of edges. So here's a graph. Every edge is assigned a capacity. So it's a non-negative number in RE, which is Rm. And the problem we'll look at, I'm going to, again, for another simplification, you could ask for more general demands. I'm going to talk about max ST flow, which is a special case. Again, these are not actual restrictions. These are just conveniences for the talk. So today we'll talk about max ST flow. So I'll give you a source S and a sink T. Every edge has a capacity. And the goal is going to be to find what's called the maximum value ST flow. So a flow is an assignment of numbers to edges. And it has to meet a couple constraints. One is that it has to have flow conservation. So think of it as pushing stuff along the edges of the graph. Flow in equals flow out for all the vertices. So flow doesn't appear or disappear. Every edge cannot exceed its capacity. And because we're undirected, this is an absolute value. So an edge can carry some amount of flow forward or backward. And the capacity U is an upper bound on how much flow you can send along an edge. And the value of the flow is the amount of stuff you send along the network. So because of flow conservation, the amount out of S is the amount into T. And that is the value of the flow is the amount you send from S to T. So our goal is going to be to send as much flow as possible from S to T, subject to flow conservation and the capacity constraints. And we're going to look at the approximate problem. So we're going to look for the epsilon approximate variant of this. So our goal is going to be to find an ST flow that's at least 1 minus epsilon times the optimal flow. So that's the problem we're going to study. It has a long history that, again, I'm going to do nothing resembling justice to. But it's been studied a lot, and it has a fair amount of previous work that I'm really not going to review. And instead, I'm just going to kind of stick with the most recent data point on it. And I'm going to talk about undirected graphs and 1 - epsilon approximate flow. And for this, the best previous running time was in a paper that I wrote with Paul Cristiano, Alexander Madri, Dan Spielman, and Xianghua Teng. And then later, there was a paper by Li Rao and Srivastava that worked in the unit capacity case, gave a sort of similar result by a very clean, kind of a beautiful different way of doing it that didn't seem to generalize to the capacitated case, but was intrinsically different and maybe a little more related to what I'm talking about today. And the best previous runtime was mn to the 1/3 times poly 1 over epsilon, and I wrote an O tilde. Whenever I write an O tilde, it means I'm just dropping log terms. And I'm going to do that pretty aggressively today, just to keep notation simple. And for maximum concurrent flow, paper that I wrote with Gary Miller and Richard Peng gave something sort of similar. So if you kind of pretend m equals n, which is really the tricky case here, like over the decades, there was a lot of improvement from, if you were to look at what changed from 1970 something till now, there was a lot of improvement in what you could do in terms of dense versus sparse graphs, or large capacities versus no capacities versus capacity 1. But kind of the thing that really seemed to be the core obstruction was just the dependence on m and in the sparse case on m, which was about n. So if I gave you a sparse graph, for a long time it was m. It was something. If you said m was like n, then it was something to the 3/2. And then these kind of were the first ones in a while that made it 4/3.
Yeah, well, 3/2 it's the exact case.
So for 3/2, there was right. So it was actually oddly enough, the best thing known to do in the exact or approximate case. And for the exact case, now there's other stuff you can do that, based on some of this and some other ideas, that pushes it a little past it. But I'm sticking to the approximate. That was sort of what I was excusing myself for with the big list. And yeah, it turns out the fact that we can't do directed graphs and the fact that we can't make this epsilon completely go away are actually strongly related questions. OK, so the best for smallish k for maximum multi-commodity flow was m to the 4/3 also. And our main result today is going to be to make the 4/3 into a 1 plus little o of 1. So for both max flow and multi-commodity flow, we're going to make our main result be something that I'm going to say is almost linear in m. And almost linear is going to mean something, so more precisely, this is what I'll give. So it's going to give a max flow result that's m to the 1 plus something little o of 1, and then times poly epsilon, where the epsilon isn't that bad here. And for multi-commodity flow, it's almost linear in m. It's still got that kind of annoying k squared as opposed to k, which maybe keeps me from saying legitimately almost linear if k is large, but for small k it is. And that's probably, broadly speaking, the epsilon is going to take something smart to fix. The k squared probably just takes a little more work. OK, so those are the main results I'll talk about. And I should mention offhandedly that it actually gives, as a subroutine, you just kind of plug it into other people's papers, and you get faster algorithms for some other things. So you get a faster algorithm for sparse cut and balanced cuts by using the Aurora Rao Vazirani relaxation solved with some iterative methods. And for example. OK, so that is my background. And now I want to actually kind of talk a bit about the content. Oh, before I forget, I should mention that this result was concurrent with another work, which was a beautiful paper. It was by Jonas Sherman, who's now finishing up his PhD at Berkeley. And he got a similar running time for the single commodity case. And it used kind of different but similar techniques. It's actually, if you look at it carefully, it's in some strong sense the dual of our algorithm. And you actually could rederive it as a dual to our algorithm. So we work with flows and he works with cuts. And when you get to the end of the talk, I can say this a little bit more carefully. But roughly, we are going to iteratively take a flow and try to make it send more flow and always have an actual flow working towards optimality. He's going to kind of go the other way, which is he's going to start with a dual object and work towards feasibility. So he's going to start with something that sends a lot of flow but isn't a feasible flow. It doesn't obey conservation, and then work towards getting rid of that. OK, so that's the setup. And what I want to do to describe the actual algorithm is actually talk about some background tools that motivated the algorithm. The algorithm itself was actually pretty strongly motivated, to some extent, by the things that we couldn't quite do with previous papers. And so I'm going to give a kind of quick background of it's not meant to be a background of actual things on MaxFlow. It's tools that we're using in our paper. So, and kind of, for the first couple decades of it, and for the fastest MaxFlow algorithms really tended to be deterministic and combinatorial. They're sort of like add an edge, add a path, push flow along this, pull flow along that, kind of things to grossly oversimplify. And those culminated in the best exact algorithm until recently and actually for some parameter ranges, still the best exact algorithm, which was the Goldberg-Rao. And I'm going to encourage you to sort of ignore many of the terms in that and just think of that as 3 halves, m to the 3 halves, just for simplicity. Anyway, recently, there's been this nice confluence of kind of techniques based on randomization, numerical linear algebra, iterative methods, continuous optimization, where the two fields really have been very strongly feeding into each other in what I think is really a growth field. Like, I think there's still a lot to do here, where there's been this very strong confluence of kind of numerical methods and numerical stuff, where instead of using discrete objects, you're going to model these as continuous problems. Then you're going to solve the continuous optimization problems using combinatorial techniques, then use the ability to solve them to feed back into graph algorithms. And it's this very nice kind of developing theory. And again, I won't really try to describe the actual literature. This is meant more just to be the things that motivate the actual algorithm today. OK, and again, I'm going to talk about single commodity pretty much entirely until right at the end. OK, so the first tool that we're going to build on, and we're really motivated as much by the tools as much by the limitations of the tools as their tools. And so what I'm going to do is kind of tell you what the tools were, tell you what they didn't do, and that's going to kind of motivate what we had to do in our paper. So the first tool we're going to build on was sparsification, which I guess I would trace back to Bengtscher-Karger. And the idea here, and these were all things that were used in the general context of things like flows, not necessarily MaxFlow. This one was, though. OK, so sparsification, the idea is just I give you a dense graph, m is much bigger than n. You don't want that. And so you're going to find a much sparser graph G prime that's going to approximate all the cuts in the original graph up to some multiplicative factor of 1 plus or minus epsilon. And the, at the time, I think fairly surprising assertion was that you can very efficiently find, and even surprising existentially, you can find a graph with average degree polylog n, so n log n over epsilon squared edges. And that actually will get every cut in the graph right up to a multiplicative 1 plus or minus epsilon. And on top of that, they came with a very nice algorithm that lets you find it very quickly. So you can find it nearly linear time. So the way it worked is it was based on a very carefully set up sampling scheme. But what's more important for the structure here is that it was a sampling scheme. The idea is that using a fair amount of graph theoretic structure, you carefully compute a probability for every edge. You then are going to independently sample every edge in the graph with that probability. And the good news, and then what you get is a much sparser graph. So you should think of it as just sampling, you're subsampling the edges of the graph. And you show that if you do it right, then every cut is going to have the right expectation and will be concentrated enough that something good happens. Now, the good news on this was that, MaxFlow min-cut theorems, if I get all the cuts in a graph right, you get all the flows right. So if I were to take this much sparser graph and solve MaxFlow on it, I will get the value of that new flow will be within a 1 plus or minus epsilon of the value of the flow on the original graph. So if I were to say to you, you want to approximate the value of the MaxFlow on a graph, this says that more or less if you're willing to tolerate some 1 plus or minus epsilon, then you can basically pretend all graphs are sparse and turn your m's into n's. Now, this is great both for this problem and for many problems. Now, the thing that kind of made it tricky for us to use in ARC setting was, and it was a limitation that we'll see why we need it later, why we worry about it later. But morally, you get the cuts right, and you get a flow on this subsampled graph. You don't get a flow on the original graph. So kind of if you think about it, what you're basically doing is every edge in this subsampled graph, which is supposed to represent a bunch of edges in the original graph, and you're relying on sampling, right? Like the idea here is if you pick stuff randomly, then things concentrate. But if I then gave you a flow on the much sparser graph, there's no obvious way to take a flow on this randomly subsampled thing and unsample it and get a flow back on the original. Yeah.
Why do it into a subgraph?
So it's a weighted subgraph. So it's a subgraph with capacities that are much larger, right? Because, I should have said, if you subsample, if you have m edges that, let's say they're all unit capacities, then you have to have a total capacity that's roughly, you have to be able to support the original flow, right? So, I mean, the weights should, yeah, so the, yeah, I mean, you should expect that the expected value of every edge is its original, the expected value of every cut is the original value. So that means if you sample an edge with probability p, it comes in with weight 1 over p. And so the weights could actually be pretty big, right? The weights, if you have a dense graph, the weights could be linear. Because you're subsampling, you're making a weighted sparse graph, right? And you have to have the average, every cut be the same size. So if you're taking out a large fraction of edges, then the average weight goes way up. And that means that actually routing on, so if you route on the subgraph, you are going to not give, you'll give a flow, but it will be on a subgraph that's supposed to represent a much bigger graph, and you'll grossly exceed the actual original capacities. I mean, it depends on what you mean by typical, plausibly n. So it's, I mean, if I were to make a graph that's like, for example, if I were to take a complete graph and an edge, then this edge is going to be really important, and this edge won't be. And so you'll get an n. I guess depending on how precisely you define typical. But roughly, the point is that you shouldn't think of these subsampled edges as actually being in a subgraph because they're scaled way up. And so and so, does that make sense? Are there any questions on that? Yeah. Yeah. Right. No, the problem is just that if I gave you a flow on this subsample graph, I just have no, I have no way to actually, even slowly, without just solving the problem over again, if I gave you a flow on a graph that's got big capacities on a small subset of the edges, there's no known way to push things back into the original graph. And this actually led to algorithmic gaps. Like, for a very long time, actually really up until these papers, there were substantial gaps between the running time for the best approximate flow algorithms and the best approximate cut algorithms. Basically, your ability to turn ends into ends, there was a legitimate asymptotic gap between how many of your m's you could turn into n's because of this. So the
approximate flow, you would get the flow or a value?
Sorry?
Approximate, you would get a flow or you would get a value?
Right, so the point is that you could get the value by solving the cut problem. To actually get a flow, there was a slower running time to get the best flow. Like, if you look at Bengtscher-Karger, maybe a paper after it by the same authors or some of the same authors, Bengtscher-Karger would let you say that it would be m plus n log n plus however long it takes to solve n log n sized, m equals n log n type problems. And so you'd get like an m plus n to the 3 halves kind of thing. And then it would become like an m root n instead, or an n root m, one of the two. So there's like an actual asymptotic gap in your ability to get to sparsify. Is that? So again, you can find the size of the cut by duality, but not the actual flow, because there's just no way to take this flow here and route it back in the original graph. Did that make sense to people? Is with me? OK, good. So that was my first tool. And the limitation we're going to have to deal with, we're really going to have to deal with this one, because we're going to want to find an actual flow. OK, so number 2 is the other kind of thing we're going to build on is iterative methods. And I'll talk about iterative methods for flow problems. So if you look at both of the m times n to the 1/3 algorithms for approximate max flow that preceded this, they all used electrical flows and the fact that you could compute them very quickly. So electrical flows basically say, take your graph, pretend that edges are resistors, somehow intelligently play with the size of the resistances, and route current through the graph, see what electrical current would do, and then do something iterative to make that into an actual max flow problem. That's solving the wrong problem. It's solving electrical flow, not max flow, so do something iterative to fix it. And they were a little bit different in how they did their iterative schemes, but broadly they both had that general model. And the fact they leveraged was that you can compute electrical current flows very quickly using Laplacian solvers. So graphs, you can associate to a matrix, to a graph, a matrix called Laplacian. Solving a linear system in the Laplacian gives you what lets you answer the question of what electrical current does in a graph. And so it turns out you can solve graph Laplacians due to some beautiful recent work. You can solve it in almost linear time, nearly linear time. So which is surprising. Like if you think about what you can get in m log n type time, m polylog n time, you can sort stuff, or I don't know, do breadth first search, or compute arbitrary linear system solutions with arbitrary coefficients on arbitrary right-hand sides using a graph based on the matrix. So it's a very powerful tool to probe the graph with, and people made very good use of this new powerful tool. Now, electrical flow doesn't equal max flow, and thus you couldn't just solve it once, but what you do is you kind of iteratively play with the resistances in the algorithm that I was on and the demands in the other one to get an actual max flow. So you'll take edges that are flowing too much and push their resistance down or up or something. And I guess the broad thing to take away from it was naively there was a root n. The actual naive analysis was root n iterations for both of them, which would give an m root n algorithm, which wouldn't be new. And then in both cases, you do something smart with your iterative scheme to make that 1/2 into a 1/3. But what's kind of important is that really the root n is the actual difficulty of the problem, and there was something smart on the iterative side, and that was really the limit of it. Like if you were to do something like this, you're not going to use the same primitive and push it farther. Like the n to the 1/3 was already by kind of tricks of iteration, and they kind of hit this roadblock. And the good news is that it's actually a nice framework. You have these very powerful primitives for probing a graph, and you have an iterative method for turning bad solutions into good solutions, right? Solutions to this bad approximate problem into good ones. But the bad news was that it really was a pretty hard root n in the quality. And that meant that it really was, the n to the 1/3 really seemed like an actual limitation of the present techniques. And so the reason I would kind of, at this stage in the talk, say this comes from is really if I give you any iterative method, every iterative method is basically the same thing, right? You want to solve some problem, you get an iteration that solves something that's vaguely similar to your problem, and then you repeat it until you get a way of crudely solving something vaguely related in an inner loop, and you just keep calling it to push yourself towards the answer. And in general, you have this crude inner algorithm that you're using to probe the complicated outer one, and the running time depends very strongly on how bad your bad solution is, right? Like how many iterations you take is always related just to the quality of the crude algorithm solution. And the root n that I said was there for real reasons was the difference between L2 and L infinity. Electrical flows minimize an energy, which is a quadratic thing. It's the L2 norm of something. You want to minimize the max. You want to make a max flow, so you want to get everything under a max capacity. It's an L infinity. That's your root n that kind of shows up. And it's really there. And if you just use electrical flow stuff, it's not going to go anywhere. OK, so that was the second one. And now the last one is the one that we're going to make the most extensive use of, which is oblivious routing. And so the first two I claim were sort of fairly obviously related to max flow, in the sense that one of them gave us a better algorithm for max flow, the other was an algorithm for max flow. This one is going to feel a little different, but bear with me. It's actually a core technical tool. And you'll notice that as I say this, it will give a very bad solution, but a solution to max flow. It will give a log n approximate answer by the end of this slide, but not one that's easy to amplify. OK, so oblivious routing, high-level motivation is you want to route. I'll motivate it the way, not from a max flow perspective, but from an oblivious routing perspective, and then we'll come back to max flow. So the idea is roughly you want to route traffic between many pairs of users on the internet. And if you're building a router, you really don't want to solve an n-cubed algorithm problem every time you route a packet on the internet. You want some sort of nice routing scheme. And so here's my internet. And I guess since it's a math talk, I should define my terms. And I guess based on empirical work, you can, if you're not familiar with the internet, based on recent traffic studies, you can kind of more or less model it as a finite capacity medium for distributing pictures of cats who can't spell. And so you have users who want to distribute these pictures. It's found other applications since then. But the idea is you have these users, and you have a bunch of sources, a bunch of sinks. And what your goal is going to be is to route stuff from source to sink subject to capacities, as before. So here we have S1 wants to route this picture to T1. S2 wants to send that to T2. And the goal is going to be to do so efficiently. But so as a general routing thing, the idea is that what is a routing? A routing is going to say, I want to send traffic from S1 to T1. And what a routing then is just you pick a distribution over paths. So we're going to think of a probabilistic. Every packet's going to follow a probabilistic route, which you could think of as a probability distribution over paths, which thus is a flow. And the idea is that you can think of, so we're not sending along one path. We're sending along a distribution of paths. So think of a lot of traffic going between the pairs, and you randomly sample. You could equivalently think of a random choice of path. An oblivious routing is going to say that you don't, solving this problem as is a multi-commodity flow problem that you can get a pretty good handle on, but it's slow. It's much slower than you want it to be if you're routing on the internet. And instead, what you're going to do is you're going to want to be able to pre-compute and program your routers. And what it's going to do is it's not going to solve some global optimization. What it's going to do is in advance, at the beginning, once you build your network, it's going to, for every pair S and T, decide how it wants to route flow from S to T. The oblivious part of it is that how a packet gets routed from S1 to T1 has nothing to do with the other network traffic. So an oblivious routing scheme is one where the routing of a single packet is, you have a fixed distribution of paths for every pair S1 and S and T. And so you'd think that this would make a huge difference, because you can imagine loading up the network with all sorts of different traffic patterns, and you'd think you'd want to very differently route certain pairs if you know that other pairs are trying to use the same edges. Right? So an oblivious routing is something where you're not allowed to use that information. Every packet gets routed independently of every other packet. So that's the setup. And it has kind of a long history. It went back to the early 80s for specific graphs. And the measure that you use here is called the competitive ratio, is the standard measure. And what it says is that there's two ways to route traffic. Way one is to solve this optimization problem for your actual explicit demands and find the single best way to route stuff between all of your pairs. That's slow, but right. Here, instead, you're just going to use your oblivious thing, which doesn't get to use this information, but you'll decide in advance your oblivious scheme, and then you'll just use it. And then the competitive ratio is the worst case over all possible pairs of all possible demands, so all possible sets of S's and T's of the congestion of your oblivious scheme versus the actual best thing you could do. And if you think about this, there is no obvious reason, at least to me, that this should be anything bounded. Right? Like, it's really, it's pretty strong if you think about it. It says that no matter what the traffic is, you can ignore all the traffic. And so there's this beautiful result that I thought was really surprising by Ricky that said that every graph G has a single oblivious routing scheme you can pick, so that the competitive ratio is log n, O of log n, which I think was a real surprise. And this is actually feels kind of nice, right? Because in particular, that says if I gave you this oblivious routing scheme for your graph, you could just say route the demand st, and then you have a flow, and you get a log n approximate flow, and that sounds great. And in fact, it even works for multi-commodity flow. So this gives you a log n approximate algorithm for single and multi-commodity flow. Now, the bad news here is actually fairly daunting, though, because one of them is that it's way too slow. Like, the best known algorithms were substantially slower than max flow. So to find the oblivious routing scheme. Depending on how you read the literature, they were somewhere between m to the fourth and m squared. Depending on if you slightly tweak constructions in the literature, I think you can get m2 or 3. The best stated ones were 3 or 4, but definitely not m, definitely much worse than max flow.
But that would be good if you wanted to do manufacturing programs with the same stuff.
Right. So it lets you do, assuming you could solve the second problem, which was that you want to get actual answers. Right. So this would still be useful if you were willing to amortize it over a bunch of computations, because you compute it once. But the other one, the one that was a little bit more crucial for this, well, both of them actually kind of are. But the other crucial problem was that it gives you this log approximation. And this log approximation is right. Like, there isn't a better oblivious routing scheme. Words involving the word flow cut gap are the things that will roughly convince you of that. And I believe that you can prove at least that there isn't, depending on how exactly you define oblivious routing, this is really an intrinsically bad thing. Like, you're not going to make the log better. And it's really not clear how to take a small number of these things and get a better flow. Right? It's not obvious how to take a bad answer to the problem and actually fix it. Yeah? Well, so so you could think.
The first one to get the
So you can, the answer is also depends on how you define it. So that was why I kind of said about, you could think of it as paths, a probability distribution over paths or explicit flows. So it's a randomized distribution of paths. You could think of it as a deterministic choice of flows.
So the maximum is the expectation.
So I defined it as choosing not a path between S and T, but a flow between S and T, right? In which case, so flow is, you can deterministically do it with flows. So think of a flow as a probability distribution over paths. And so it's a deterministic thing where you route flows. And so I think it's a little bit cleaner to talk about, instead of talking about probability distributions of paths, talk about deterministic choices of flows, which implicitly are saying expectations, but they're, because I'm using congestion and flows, I've dodged having to put another round of expectations in. That, other questions?
So how is this shouldn't the min-max imply that if I choose the right
No, it's just the lower bound was what deterministic. It does nothing
Meaning a
to do
single
with
path.
minimax is already for probability. If you allow only deterministic paths, right, not closed paths, that was the lower bound. For every pair you decide on one path. This is always
Right. Is that everybody happy? Okay, good. So that's the setup. And largely, our whole algorithm is motivated by just kind of trying to cross off the limitations here. And so our new technical primitives are going to kind of solve each of these separately, basically. So for sparsification, which we're really going to need, what we're going to do is introduce what we'll call flow sparsifiers, with slight apologies to other people who have used the same word for other things, but we couldn't think of a better word. So we're going to call these flow sparsifiers. And what they're going to do is they're going to give you a sparsification scheme along with the ability to efficiently route, not just that you get the cuts right, but you also get an actual way of efficiently routing things back in the original graph. With a little bit more of a loss, but we'll talk about that. So
which is stronger than the normal cut sparsifier.
yes, it will be a cut sparsifier plus a routing, plus an efficient routing. Yeah.
Doesn't that solve the problem?
It still is. I mean, the efficiently is going to. Oh, okay. So I guess I should be careful in how I said what we got. So it partially solves it. What it gives you is the ability to sparsify. So it gives you the ability to turn dense graphs into sparse graphs, but it doesn't give you the ability to solve the problem on the sparse graph. So this solves the problem of, given the answer on your sparse graph, getting one on your dense graph, but for sparse graphs, it's still m to the 4/3 or 3/2, depending on how you count. Yeah.
Did you mention where things go wrong for everywhere?
Yeah, the short answer is kind of everywhere, but the longer answer is, well, if we were able to make, so, okay, here's a unsatisfying answer, and then later in the talk, afterwards, I'll give the more satisfying one once I've put some of the machinery in place. But I guess one answer is the oblivious routing completely doesn't exist. So the actual competitive ratio guarantees for directed graphs are not there. Maybe another way of saying it is that actually, it turns out that max flow on directed graphs and max flow, when I say exactly, max flow with a log 1 over epsilon dependence are equivalent problems. So if you could do directed graphs, then you could do exact, log 1 over epsilon running time and vice versa. And so in some sense, I would say one answer to your question is if we could get a better epsilon dependence, then we'd have it. The other one is that the words we're using, at least, like oblivious routing and competitive ratio, if you define them in terms of directed things, they just have lower bounds that make things break badly. And then later I can go back and gesture at things to say which things break, but is that probably? Okay, good. So flow sparsifiers will be our first tool. The second tool we'll have is just an iterative method. So again, we had this, what we're going to do is we're going to take these iterative methods, we're going to describe a general scheme for iterative methods that's not going to use L2, right? Like, gradient descent is kind of one way of doing iterative stuff. It's really kind of got L2 hard-coded into it, and that root n is then not going anywhere. Maybe it's going to 1/3, 1 to 1/3, but not any worse. And so we're going to describe what I'll call non-Euclidean gradient descent. And we'll use this to reduce the problem. I'll use this to show that you can actually take max flow and turn it into oblivious routing. So I'll use it to reduce the problem of solving the flow problem to getting a good oblivious routing scheme. And then so the idea is we'll then give you a fast oblivious routing scheme. And then the iterative method will let you fix this you can't turn crude into exact problem. Right? So the iterative method will take the ability to use a decent oblivious routing scheme and repeatedly call it to get a good max flow algorithm. So and I should say this one, the really new part is the reduction. Using it is how you use it to solve max flow with oblivious routing schemes. It's nominally new, but not really new in the sense that there's a number, like for the actual iterative method, we couldn't find someone who formalized it in a way we liked and could use black box. So we reformalize things in what we think is a nice way, but there's a non-negligible number of people who wouldn't be surprised by the general iterative methods. But we kind of repackaged it in a nice general way. And the new part really is more just how you use oblivious routing to solve max flow. Yeah. So it's, I'll define it in a sec. But yeah, I mean, what I mean by that is using your iterative steps are not going to be over L2 balls.
No, but it's in some other L.
In some other ball, yeah. Yeah, and so it's still greedy. And actually, yeah. So I'll define it very exactly on the next slide, but yes. And then kind of ideological point that I wanted to push here was just that you'll notice that throughout the talk, what we're doing is we're going to be using the graph structure. We have this iterative method, which is a continuous object. And we're not going to use the naive basis. We're not going to write things in terms of vertices and edges. If we did as our sort of basic objects, we'd more or less get stuck back with the previous algorithms that would do electrical flow. But instead what we're going to do is we're actually going to more carefully use the graph structure to get the right representations of our, the right numerical representations of our objects. And actually, I think this is maybe one of the crucial insights in the field right now is that, I think if I wanted to make a slightly risky assertion, for almost every problem, I think the edge vertex basis is the wrong one to use for almost anything. So here we're going to find a better one, and that better representation is going to give us a lot of the power. OK, and then the last thing is, by now I guess not a surprise, we're going to give a fast oblivious routing scheme. So we're actually going to show how to get an n to the little o of 1 competitive oblivious routing scheme that runs in almost linear time. So it runs in similar time. And the n to the little o of 1 you could push to a little better. You could push it to something like n polylog, but we're not going to because it's not necessary. OK, so that's the setup. So again, the high-level setup, these are our main tools. And what's going to happen in our approach is going to be we're just going to put them together. So I'm going to now, for the rest of the talk, make all my capacities 1. This is just for notation. In the paper, we write it with capacities. It's just cutting down letters here. So the first thing we're going to do is we're going to just rephrase the same problem. So instead of trying to send so every edge has capacity 1. Instead of saying we're going to send as much as we can so that no edge flows more than 1, excuse me, we're going to just rescale it and say we're going to send 1 unit of flow and minimize the max over every edge. So we're just going to divide things down by the answer. So the problem we're going to solve is find the unit st flow. So send 1 unit of flow from s to t, and you're going to minimize subject to that, the most flow over any edge. And then our algorithm is going to be kind of, I guess, not a surprising one at a high level. Start with some flow and fix it. Yeah?
If you send only 1 unit flow, I mean, how can the congestion be higher than 1?
Oh, it won't be, but you're going to minimize the number. You're going to, so you're going to,
Minimize the n number of edges?
you're going to minimize the maximum amount of flow on any edge. So if I were to tell you that when you send 1 unit of flow, no edge flows more than 0.2, then that tells you the max flow is 5.
Just scale it. Oh, just scale it. The max flow was there because they like dividing everything, right? Oh, I see. It's not that you can send only discrete.
Right now, there's no integer requirement here. So yeah, you're just dividing by the answer essentially, and it's just more convenient for the iterative scheme. And then what we're going to, so our whole algorithm is really just start with some guess, make it not atrocious. It's not going to have to be too careful, and then repeatedly fix it. And the way we're going to fix it is we're going to take our present flow, improve it, repeat. And the high-level structure is that we'll have, excuse me, n to the little o of 1 iterations in each iteration. So I wrote this. This is the actual answer. It's 2 to the root log n log log n. The way to think of 2 to the root log n, I guess, is take a log of it. So you'll see that it's between polylog and a polynomial. So it's strictly less than any polynomial, but strictly more than polylog. So that I'm just going to write n to the little o of 1. And it's going to take similar amounts of time. So each iteration takes m to the 1 plus little o of 1 time. And the number of iterations is n to the little o of 1. So that gives you the asserted result. OK, so the two main parts now of this are going to be, as you might guess, the iterative scheme and the inner loop. The iterative scheme is this non-Euclidean gradient descent, which we'll use to reduce the problem to constructing a certain matrix with a certain set of properties, which I'll describe in a sec. And then this will be, I'll call it a projection matrix, because it is. And then given the projection matrix, given this setup, the iterative scheme is going to say you need to use this projection matrix a small number of times, and then I'll say how to construct the projection matrix. And for that, by that I mean you'll be able to multiply by it fast enough that you can actually use it in an algorithm. OK, so the outer loop is this iterative scheme, and the inner loop is constructing this projection matrix. And the projection matrix, it's going to be an easy calculation to say that the properties we need from this congestion matrix will be, you can get them from a good Oblivious routing scheme with good competitive ratio. And then the harder part is going to be actually constructing the Oblivious routing scheme with the necessary properties. So I'll do all these in a bit of depth, but the, I guess, super high-level picture here is we're going to start with our graph, and we're going to do routing by recursively reducing it to simpler and simpler graphs until something good happens. Oh, right, and flow sparsification is going to come in the recursively reducing it. We're going to have steps to make the number of edges smaller and the number of vertices smaller that will kind of trade off against each other. OK, so that's the very high-level picture. Again, it's iterative scheme constructs projection matrix. Projection matrix comes from Oblivious routing. Oblivious routing comes from flow sparsifiers and a whole bunch of other stuff. So let me quickly run through the gradient descent. And it's basically what you'd think gradient descent should be, but with a slight tweak. So generally, gradient descent, what we're going to look at is we're going to try to minimize a convex function, f, high-level picture, start at some x, improve it. Right? So take x to x plus some delta. And generically, it's just something that makes your f better. Standard gradient descent says the thing you're going to use is the gradient. Right? And the way I want to phrase it is think of your function f as its value at a point plus a linear term, gradient of f dotted with the displacement, plus some other stuff that's smaller. That really should be a little o, or else not a super interesting assertion. And right, so it says linearly approximate your function. And then what gradient descent says is you look at a ball around your present value. So you take an L2 ball around where you are. Take r small enough that your linear approximation is still pretty good, right? That your function is well approximated by its gradient. Then find the point in the ball that minimizes your linear approximation. And say your function's pretty close to its approximation, and you're minimizing the approximation. Thus, you're making progress on your function. And then you repeat, right? And so if you were to write it out, it says what your new step is going to be, your new point is going to be, is you're going to take the min over all points in a ball of some radius that's small enough of the linear approximation of your function. And because L2 is nice, it turns out the answer to that is actually the direction you want to go is actually the gradient. But note that the gradient here was the direction, not by necessity, but because if you minimize v dot x over the ball, you get something in the direction of v. OK, so all we're going to do here is just do gradient descent for general norms. So the idea is that same thing, but we're not going to look at an L2 ball. So we're going to step in the direction of the thing that minimizes the same quantity, the linear approximation of your function, but like we're not going to use the L2 norm. We're going to use some arbitrary norm here. So for any norm I put in there, I can do the same thing. Now it's no longer in the direction of gradient of f, actually, because you could be minimizing over something other than a ball. And what you really need to have, just I'm going to give a little bit of notation, is the right thing to work with is the dual norm. So the dual norm, I'll write a little star, is of a vector z is the maximum over the unit ball. And again, when I use these double bars, this is an arbitrary norm, not an L2 norm. The dual norm will just be the max over that ball of z dot y. Sorry. And OK, so I gave you the dual norm so I can define the qualities we'll need. And the qualities we need are, I said that what you'll do is you'll pick some r where your approximation is good. I need to tell you what that approximation is. And what's going to govern how far you can go is how quickly the derivatives change, right? But here, it's not just it's not second derivatives. Those are sort of tuned to L2, right? What it's going to be is how badly the gradient can change over the ball that you actually are looking at, which is now not round. So we'll define the Lipschitz constant of the gradient to be the smallest L such that, and the dual norm is the right one to put there. You should just trust me or check it. But the idea is that you want to measure, you look at the dual norm of the gradient between x and y, and you'll say the Lipschitz constant is the worst case of the ratio between how far away x and y are and the dual norm of the change in the gradient. So the way to think about that is to think about essentially how much the gradient can change over the unit. Like you're taking a little ball in your norm, and you're going to ask how far can you go before the gradient changes a lot. And the way that we care about the gradient is what it does, is how bad it is as an approximation of the objective function.
Here are you computing this L only for a ball of small radius or for any x and y? This is the definition of, it depends on f or f and r.
Oh, the Lipschitz constant will be a global, it will be a function only of f.
Only.
I mean, really, it's only of f's that you'll ever see in your algorithm, but we're not going to, like, but
Anyway,
here it will be, yeah.
depends on the size of the ball.
Right. You could do that more carefully with a general setting, but we won't need it. And then we're going to define this thing x sharp. And what it's going to be is it's just going to be the point that says you're going to, this is roughly saying take your best step. It's going to be the max over x over all s. So instead of saying maximize over a ball, what we're really going to do is say pick the, we're going to let the radius be chosen kind of by minimizing this. So here you have objective function, and here you have penalty for being far away. So you're going to, sorry? Well, I think in the way I did this, actually, I made x be your original point and y be your new point. Right? Oh, I see what you mean. Yeah, y should be x, right. Sorry. Good. Like I said. Thanks.
Is this completely like steepest descent, like in Boyle and Van Bergen, or is some?
If I made this all with Euclidean norms, it would be straight steepest descent.
No, steepest descent with any norm, right?
Yeah, the analysis, the exact guarantees of the analysis are a little tweaked, is why we did this. It's very close to the standard write-ups of these things, but the way that, in a second, the guarantees that we get out of it were just phrased in a way that was more convenient. So it was just how we defined all the constants and stuff. So the answer is, as I said, like I couldn't find it verbatim prepackaged, but I'm sure that if I told this to Boyd, he would not be surprised by it. Right? It's more an organization, not a new result. And anyway, so now the algorithm is this, right? The algorithm is take a step scaled by the 1 over L in the direction that this thing tells you to do. So really it is draw a ball around your point, take a step, repeat. And that's it. Now the quantities we're going to need to define. So what governs the running time?
One question. Why,
Yeah.
I mean, in the standard linear descent, we use the fact that indeed every function is approximated by this linear function plus something different or the two norms.
Right.
But when we work with different norms, I mean, do we have any similar guarantee?
Yeah, we're going to use the same linear approximation, right?
But then the small O term depends on the L2 norm, right?
Which will still be small o. I mean, it will still, you'll get, so we're going to use the actual linear approximation of the function, which the right thing, that is the right, if you're approximating a function by polynomials, L2 is the right way to do it. And then there is a unique answer to the right linear approximation here in the space of linear functionals, right? Like there's only one answer to that part of the question, but the optimum over the ball is the part where we're using the norm. So, right, like if you were to linearly approximate a function, there is a right answer here that in the space of gradients, right, in the space of forms, and then we're using the norm just to actually get a step, and that's where the norm's showing up.
But this choice is what breaks the barrier of time. This choice of the ball, of the norm, is what
Yeah, it's one of the pieces, yeah.
That's the choice of this one.
And the construction of everything. But yeah, right, like morally, you can't hope to get from one corner of a cube to another corner of a cube if you put balls inside of it, so we're putting cubes inside of it. Right, like, so we needed to, the iterative scheme was, the fact that we're searching over L infinity balls was necessary, right? But the idea is that there's two parts. There's approximate your function and then optimize your approximation. And so we're using the standard, the only way to linearize the function, but then we're approximating it over the box, we're going to use L infinity as our local norm. And that is what's going to, the root n is coming from the fact that if I just kind of take only steps in balls, cubes don't look like balls, and there's a root n there. So we're going to use cubes inside cubes, and it will be better. Yeah, so again, the way we're using the norm is in this part of it. It's not in choosing the approximation, it's in choosing it's in what you do with the approximation. We're maximizing it over a local neighborhood defined with the ball.
This is norm you're going to use as L infinity?
We're going to use L infinity for our local norm, yeah. Yeah.
Is there any natural lower bound for the number of iterations of elements? Like, gradient descent?
So if you do just gradient descent, there are lower bounds for this class of, if I give you oracles that meet certain properties, then given that, there are lower bounds. Roughly, the analysis that we're giving will be tight for a thing that only obeys exactly what we're giving it. So if you're only allowed to do what we're doing, compute linear approximations of things, this is going to meet the lower bounds. But there's no general lower, depending on how, if I give you, to specify it properly, you have to say, here's what I'm allowed to use. And if all you're allowed to use is first order methods, then there are lower bounds. Sorry, this is not going to meet them uniformly because there's a slight speed up you can do for some of these norms. Like for L2, there's this thing by Nesterov that does accelerated coordinate gradient descent, which is actually a little bit faster, but not much faster. And we couldn't get it. We actually don't know how to make it work in the L infinity setting with the useful set of guarantees. So the answer is there are lower bounds. Gradient descent is not the best first order method. Our analysis is right for the analysis of gradient descent. It's off by a square root somewhere, carefully chosen for the analysis of any first order method for L2. And for L infinity, we're a little fuzzy on exactly whether we can get that square root to happen. Yeah, a square root of so the difference between k and root k iterations. For us, it's going to be the square root of something that's n to the epsilon, so it won't matter. When you're, I guess the right analogy is think of the difference between conjugate gradient and gradient descent for linear system solving. One of them takes the condition number, the other takes the square root of the condition number. It's actually the Nesterov things are very strongly analogous to conjugate gradient. They're primal dual, but we don't. There are some substantial technical roadblocks to making them work in this other norm kind of setting that we don't know how to get past. So we're just using gradient descent. Other questions? Okay, so that's our setup. And the thing that's going to govern it, its running time, is just going to basically be, if I tell you here's how big your steps are allowed to be, then there's a diameter of how many little blobs that you're allowed to take steps over that it takes to get from one side to the other, and that's what this R will be basically. So we'll say you'll take the max over all x's in space and all points that you might ever hit in a gradient descent thing, so you're only going lower, so you can look at stuff whose values are better than the starting point of this thing, the number of steps you need to take, basically. So this is just a lower bound of diameter if I tell you your step size, if you work it out right. And after k iterations, you can show that this is kind of the main point, your distance from your optimal answer. So x star will be the actual solution you're trying to find. The optimum, you'll show that your objective value minus the optimal objective function value is going to be bounded by some stuff that falls off linearly in k. So k is the number of iterations, and the numerator is LR squared. It's a function of the Lipschitz constant and the radius.
What's the time complexity of executing every step? Suppose you're using infinity norm.
So that the step is, so in general, it's one matrix vector multiply with your gradient. I'll say in a second in our case, it's very simple. It's compute the gradient and minimize it over your norm ball, and depending on how good an access you have to the ball and your norm, if it's the infinity norm, you just take the biggest coordinate. It's not complicated. I guess if I gave you a complicated enough norm, I'd have to talk about oracles. to give you a good answer, but it's a very simple step, is the point. And for us, it's going to be dominated by computing one matrix vector multiply, too. OK, so let me actually say it here, and then I'll instantiate it. So for max flow, we're going to just instantiate this scheme for our max flow problem. So I'll define this matrix B to be the edge vertex incidence matrix. And so by that, what I'll mean is just my last piece of notation, I think. But what I'm going to do is it's just going to be something where rows are edges, columns are vertices. And for every edge in the graph, you'll have a row of the matrix, which will have a 1 and a -1 in the things corresponding to the vertices. And it doesn't matter what order. You just arbitrarily fix which one's the one. Like, you're going to arbitrarily fix which is the one and which is the -1, and it won't change anything. It's just a sign convention. And so this is our edge vertex instance matrix. So 1 and a -1 for the 2 vertices involved in every edge. So it's an m by n matrix. And it's convenient in that it lets us write things about the demands routed by a certain flow. If I gave you a flow f, so a vector on a number on edges, then B transpose f, you can convince yourself, is what I'll call the demands. It's the so it's the net. It's a number per every vertex. That's the net flow out of the vertex. So here we want B transpose f to be like 1 in S and -1 in T and 0 everywhere else. And so B transpose takes a flow, produces the demands routed by the flow, which you could think of as a vector of net flow out of each of the vertices. So we can now write our problem as this, right? It's going to be minimize overall flows such that they route the right demands, the infinity norm. I'm going a little slow, so I'm going to accelerate a bit. But so this is an algorithm, right? So the idea is if I start with any initial flow that routes the demands, which you'll find by something not too complicated because it's not supposed to be that great, then you're going to minimize the infinity norm of f0 plus gamma, where gamma is a circulation, right? If I route the demands and then I look at everything that routes those demands, their difference is going to route nothing. It's going to be a circulation, which it means B transpose gamma is 0. And this is not exactly how we're going to do it. So roughly, the constraints are going to make things a little annoying. The such that thing here. So what we're going to do instead is instead of parametrizing it like this, we're actually going to do an unconstrained problem where we're going to, instead of forcing gamma to be a circulation, we're going to project onto circulations. So I'll define P to be a circulation projection matrix. It's m by m, and it will have 2 properties. One is if I give you any flow, it projects it to a circulation. So B transpose PF is 0. And the other is that it routes any circulation to itself. So if I give it a circulation and I project it, it stays the same. So these are, it's just a projection onto the space of circulations, a linear projection. And we're going to solve the unconstrained problem of minimizing f plus pc. So instead of forcing it to be a circulation, we're going to let c be anything and then then apply p to it. Now, the one thing I want to be a little careful with here is note that P is not necessarily symmetric. P is not the L2 projection. It's an arbitrary projection matrix. So it's a non-symmetric matrix, possibly. And if P were equal to P transpose, this would be orthogonal projection onto the space of circulations. And we'd basically get the previous algorithms. But instead, we're going to use, I'll call it an oblique projection. I tried to draw a picture of it's a not orthogonal projection. So it's a linear projection. It's a linear operator that projects onto the subspace, but not necessarily orthogonally. And this, yeah. So it's not an approximation, right? It's that you could think of it as orthogonal, as an orthogonal projection in some other norm, some other L2 type norm, right? It's we'll see how we construct it in a sec, but if you use straight orthogonal projection, you're going to end up with standard L2 gradient descent. Basically, you're going to be computing electrical flows. What we're going to do instead, so standard projection will be electrical flows, and then you'll get stuck with all the problems they introduce. Instead, we're going to construct our projection matrix using combinatorial structures of the graph. And we have additional freedom now in how to do it, because we have a whole class of ways to project. So all we just needed was that it's a thing that lets us parameterize our space by PC. But it's not an approximation. It's an exact thing, but it's an exact thing constructed very carefully, and this is where I said you're using combinatorial structure to describe your numerical parameterization, and it is crucial. So if I gave you a circulation projection, I claim we'd be in super good shape. Because what you do is you'd write down the minimization problem we had. Now it's straight unconstrained, because we don't have to force the thing to be a circulation. We just project it into circulations. OK, little issues. The first issue is that L infinity is not really good for gradient descent because it doesn't have gradients. It's not differentiable. Not a huge deal. That one, I don't know, use subgradient or something was my answer to it. Like, there's ways to get around the corners. But there's a bigger problem. The bigger problem is that the gradient, even where there are gradients, is just the wrong thing to use. And the problem is that it picks out the biggest coordinate, even if the others are close, right? Like, if I were to look at the derivative of the infinity norm at a point like 100 and then 99.999, and then a bunch of zeros, it's going to say you want to decrease the first coordinate. And it's just not going to see the second coordinate, because the gradient will just be in one basis direction. And that's really bad, right? You could, it will basically fix one coordinate at a time in some worst case, in which case you'll get a lot of iterations. Morally, you want to kind of fix both of the first two and not the others. And so there's a standard answer to this, which is to replace L infinity with the softmax function, which is like the max but softer. And it's just a thing with a bunch of exponentials in there that blows up. I'll write the properties we'll use of it, but if things are markedly different in size, then it becomes the max. But when things are roughly the same size, it lets you actually take steps in all of them. So this is the function. Sorry? So this part of it actually, we could almost write our paper with multiplicative weights. We would have needed a weirder oracle guarantee because we needed, so you wouldn't actually be able to use an oblivious routing scheme because you wouldn't be able to change. There's one, you'd need an extra degree of freedom in it. I'll answer this offline or at the end just because I want to get through this. But multiplicative weights you could do with not an oblivious routing, but another oracle that was a little more contrived feeling. And this is roughly paralleling something that you could make, like you could do this with multiplicative weights, but it would require oblivious routing plus a little bit more stuff in your description.
That's what Jonah does now, right? He's done doing everything with multiplicative weights.
Not in print, but hopefully in print one day.
Yeah.
And so, yeah, the other thing is that the way that if you do it with multiplicative weights, at least in his current version, he loses a little bit on the running time. Like, he loses some epsilons and stuff. I'm not sure if you can fix that. Maybe you could, but at least as is, his paper has an extra epsilon floating around that you can get out with a gradient descent analysis. I suspect if you did multiplicative weights right, you could also get rid of it, but I don't know for sure in his paper. Because there's these phases that you have to do, and those add on an epsilon and a log. Anyway, right, so this is broadly similar in terms of what it does to multiplicative weights, but not quite. And yeah, in Jonah's actually, it's there's a much more natural mapping to multiplicative weights here. It would feel a little bit contrived, I think, but it would still exist. And this looks a lot like the stuff that shows up in multiplicative weights. OK, so in case you're wondering, that's what the t is in these expressions. It's a thing that's tuned to make those about the right size so that they blow up when things are bad. OK, so here are the properties we're really going to need. The properties of this that are all just calculations is one is that the infinity norm, softmax is close to the infinity norm, in the sense that it's above bounded by the infinity norm and lower bounded by the infinity norm minus this t log 2m. So t here is epsilon times opt over some logs. OK, good.
So you don't know what opt is, so how do you say?
Let me get back to that. I'll get back to that in the end, but it's not a huge deal. Yeah. We could do a little better, but yeah. We can do a little better because we both have a sense of what opt is, but yeah. Right, so then the next thing is Lipschitz constant of the gradient in this thing. So the nice thing about this softmax thing is that it's actually tuned to be good with gradient descent in the infinity norm, rather. So L2 things are nice for L2 gradient descent. This function is the thing that works nicely for L infinity gradient descent. So it has the property that if you were to look at our definition of Lipschitz constant, it's good for infinity norm gradient descent. Excuse me. And right, so the softmax, therefore, of f plus pc, if you just do the calculation from the previous thing and take some derivatives, you'll see that the Lipschitz constant of f plus pc as a function of c, remember f0 is a fixed constant, is the infinity norm, the L infinity norm squared of the matrix P, the infinity to infinity norm. So I feed it vectors of infinity norm 1 and look at the maximum infinity norm of what comes out. Then if you just compute use the previous line, you can compute this. And so the Lipschitz constant of our function, f0 plus pc, its gradient is the 1 over t from that. And then the numerator is this p infinity squared. And so our goal is going to be to do that. It's going to be to find something with small p infinity, and then we're in good shape. So given all of this stuff, what we've done is we've reduced it to constructing a circulation projection where the iteration bound is some nice function of p infinity. And all you're going to need to know is it's polynomial, because we're not going to worry about how many log factors we get, and we're only going to, the infinity norm is going to be small enough that it won't really matter. So what we'll do is if I could give you a matrix P with infinity norm that's n to the little of 1, then I will get an epsilon approximation in n to the little of 1 poly 1 over epsilon iterations. And then we'll be in good shape. Assuming a whole bunch of things like that, we can actually do it quickly. Yeah?
The reason that you can't take symmetric projection matrices is that you won't be able to find projection matrices, symmetric projection matrices.
There's really only one projection matrix if you do symmetry, and it will have a root n in the
It won't have this small
Lipschitz.
infinity norm.
Yeah, it'll be a root n.
Oh, okay.
So you'll basically get back to the unaccelerated versions of the previous 4/3 papers. You'll get the 3/2 kind of running time. So the point is we're going to construct our projection matrix to match our goal. Are people with me on all this? OK, so now there's another line of this that's going to say, I claim projection matrices and oblivious routing schemes are the same thing. I'm running a little bit over.
10 minutes.
Sorry?
10 minutes, okay.
Is 10 more minutes OK? Yeah. OK, and then 10 more minutes I could do it. Sorry, I think I didn't. Yeah, OK, good. OK, so this next stage is just, now we have projection matrix and we're done. Right? Then we just call it a bunch of times. We're going to construct it. I claim only kind of just by messing around with semantics, we'll be able to reduce constructing a projection matrix to constructing an oblivious routing scheme. So what we're going to do, so let me tell you how to define an oblivious routing. And I should give the warning, I'm going to define only linear oblivious routings. So when people talk about oblivious routings more generally, they might not be linear. So I'm giving a linear oblivious routing, and I'm going to forget to say the word linear probably. Don't worry about it. There is a more general class, and some things I say might be only true for linear oblivious routing schemes. OK, so a linear oblivious routing is an m by n matrix, an operator that you feed it demands, and it spits out a flow. And the way it does it, it's going to have the property that B transpose A chi is chi. So what that means is that I take chi are my demands. A chi is a flow that routes the demands that I'm given. So that's what I mean by a routing scheme, right? It's you give me demands, it gives me a flow. And the competitive ratio is the competitive ratio defined before. And if you were to now let's kind of expand stuff out. So B transpose, so just make sure, I'm just going to put this all up in one shot, right? So I'm going to now compute the competitive ratio as an algebraic quantity. And so B.
That's the definition of the operator A is the inverse of this one. So every demand vector is
It's any
sorry,
random.
it's rectangular. So
Yeah, it's rectangular, right? And then, but yes, if I were doing, and also, yeah, you could, if you did that the right way, you could get a linear projection, standard L2 projection. But yeah, these things get a little bit fudged together when you're doing not standard projection. OK, so B transpose maps flows to demands. The oblivious routing scheme A maps demands to flows. So if you want to look at flows to flows, you'll get A B transpose. So A B transpose maps flows to flows in a way that preserves demands. And I claim that if you compute the competitive ratio, it's just the infinity norm of the matrix A B transpose. Roughly, the idea is you take the actual optimal thing to do, feed it through A B transpose, and you look at how bad that is. And there's only one your oblivious routing scheme that will route the same demands and not be any worse than that infinity norm in terms of congestion. So the important point here was now we've actually, we can measure the competitive ratio as just the infinity norm of AB transpose. And note that, conveniently, if I take I minus AB transpose, it's a circulation projection, right? Because it routes the A, B transpose routes the demands. I routes the demands. I subtract, and I route nothing, right? I get a circulation. So this matrix P of I minus AB transpose is a circulation projection. And the infinity norm of the circulation projection is the one coming from the bounded by 1 plus row of A. So in particular, if I give you a small row of A, I give you a small infinity norm, which gives you a good bound on our iteration count. And so that actually means that now we've reduced the problem of constructing a projection matrix to constructing a good oblivious routing scheme, where the cost of each iteration, this was the answer to your question from before. So the number of iterations depends on the competitive ratio, which makes a lot of sense, because the competitive ratio says it's the ratio of how well you should be routing demands to how, in the best case, to how well you actually do, which is how crude your oracle is, and thus how many iterations should be related to it. And then the cost of each iteration is going to be dominated by matrix vector multiplies with P and P transpose. And so our goal is going to be to get row small and the multiplications to be fast. And so the rest of the talk will just be to sketch a construction of an oblivious routing algorithm, A, such that these things are good. So row of A, the competitive ratio is going to be m to the little o of 1. And the time to do it is going to be time to apply it. Note it's going to be a little bit, it's almost going to be linear. It's going to be m to the 1 plus little o of 1. And so putting that together, that will give us, you then will have to call this thing m to the little o of 1 times, and you'll get the claimed algorithm. I'm just going to give a notation to have it. I'm going to write T of A for the time to multiply by P and P transpose, the worst of the two. So that's our goal. And the overview, this I'm going to really sketch, because this is where a lot of the technical work is, and this one's going to have some sketching. But I want to give you the basic picture, which I think is pretty clean. So roughly, to oversimplify previous stuff, oblivious routings, what they do is the way most of the previous schemes worked is they routed using a probability distribution over trees. If I give you one tree, it specifies a unique way of routing any demands. If I give you a probability distribution over trees, that's an oblivious routing scheme. It gives you a flow. And the idea is that the reason that you ran into these major problems with using previous stuff, like the reason that m squared was not going anywhere, was that you could actually prove to get a decent competitive ratio, you actually need at least m trees. And just to write down m trees takes m squared. And so that's bad. And so even writing down the answer is too slow. And so the solution is kind of obvious in that setting, right? You don't write them down. And so what we're going to do is we're going to describe them implicitly and recursively. And so the way we're going to do that is by kind of recursively reduce routing on one graph to routing on better and better graphs. So for that, we'll need one more definition, which is just which is going to be the following. So suppose I give you two graphs on the same vertex set. I'm going to talk about how to route one on the other. So if I gave you their incidence matrices, then I'll define an embedding M to be a matrix, an M prime by M matrix, so that B prime transpose M equals B transpose. So unwinding what that means, what it says is I take every edge of G and I route it on G prime as a flow. So morally, what we're going to do is if we have a routing of one graph on the other, then you can take a route on the first graph and then push it through this embedding to get a routing on the second graph. And the congestion is going to be what you'd think. It's the max over all edges of the amount of stuff routed over an edge in the original graph, in the new graph. And so our theorem is going to be, the whole oblivious routing scheme is going to involve two things. One is going to say, take your graph and reduce the number of edges. And the other is going to say, reduce the number of vertices. And we're going to repeat them. So the edge reduction thing, and I'm not going to quite say the word embedding in certain cases because it's almost an embedding, but not quite. I'll say that in a sec. It's a couple lines away from an embedding. But OK, what the idea is I'm going to given G, and I claim you can find a G prime in almost linear time so that the new graph is sparse. So this is our theorem, and it's going to be very close to flow sparsifiers. So I claim you can construct a sparse graph and it will come with the ability to route stuff back. So it will come with, given an oblivious routing scheme on the sparse graph, you'll be able to pull it back to an oblivious routing scheme on the original graph. And the running time will be linear plus the time to do the other oblivious routing scheme. And also the competitive ratio won't blow up much. It'll be up to some log factors, the same as before. OK, so this is one of our pieces. The other piece is going to be vertex reduction. So this says I give you a dense graph. I can reduce routing on it to routing on a sparse graph. The vertex reduction thing is, and the only reason I did it as a reduction instead of an embedding is just because of kind of little silly algorithmic concerns. Think of it morally as an embedding. But I just wanted to be able to actually state running times and stuff. OK, so for vertex reduction, what we're going to do now is we're not going to route one graph. We're not going to reduce routing to routing in a graph with fewer vertices. We're going to reduce it to routing in a bunch of graphs with fewer vertices. So the idea is what you'll give me a graph G, and I'll give you T graphs in time O tilde of Tm time. So I'll give you a bunch of graphs and reduce routing in the first one to routing in the others. So in the previous stuff, think of it as a distribution of trees. I'll reduce routing in my graph to routing in n trees, or m trees. Now we're going to, instead of going all the way to trees, we're going to go to simpler graphs, but not quite trees. And that's where we're going to kind of get the recursion. So vertex reduction is I give you a bunch of graphs, T of them. Each graph is going to have O tilde of m over T vertices and at most m edges. And given an oblivious routing on each of the new graphs, you can construct an oblivious routing on the original graph with the running time that you kind of want. It just add up all the numbers. So no real loss. And the competitive ratio is going to be just bounded by the worst competitive ratio with some tildes. So if you look at these two things, the way to think about it is if you look at the second one, this says that if I give you that the amount of complexity of routing on this new thing, it's going to depend on m, right? So it's m over t. So if I gave you a dense graph, bad things would happen, right? This says complexity, it reduces the number of vertices in terms of the number of edges of the original graph. This reduces the number of edges to something sparse. So what you do is you just interleave these, right? You're going to say, take a dense graph, create a sparse graph, use the sparse graph. Now this is much smaller. That gives you a distribution, and then you repeat. And that's the whole, and then put those into a simple recursion, and you'll get the algorithm. So actually, I claim these two things, just plus writing out the recursion, is all you need to do the whole thing. And I just have to give you those two pieces, and then you're done. And so the reason we needed them, edge reduction was because the vertex reduction had an m there, not an n. So otherwise, we'd be in trouble. And the extreme case of the previous one was just trees. It was making these smaller graph trees. What we're going to do instead is not go all the way to trees, but just go to simpler graphs that aren't trees and then recurse on them. So OK, flow sparsifiers. The main tool is they're almost syntactically equivalent to edge reduction. I actually do only have 4 minutes left. This is surprisingly fast. So a flow sparsifier is going to be the object we'll construct. That's basically the edge reduction lemma, but more or less. So what it's going to do is you give me a graph. It's going to spit out a new graph on the same vertices and give you an embedding of your new graph into your old graph. That's the new piece. And the properties it will have, one is it's a sparse and a cut approximator. So this is just the standard stuff, the standard cut approximation things. And notice a 1 plus or minus epsilon cut approximation. And then on top of that, it's going to be a flow approximation. So what you're going to have is not only do you have that your new graph has all the cuts about right, but also it's going to come with an embedding of the new graph into the original graph so that the congestion isn't too big, bounded by some alpha. And that's a parameter of your construction. Right? So it's kind of what you'd expect. So this will be weighted, yeah. And the other thing we're going to want on it is that it's fast, right? So the last parameter on this list is just how long it takes to do it, and we're going to require it to be O tilde of m, so almost linear. And our theorem is that we can construct an O tilde of n epsilon O, I want to say O hat, rather. That little thing that means like n to the little o of 1, not quite log factors. Sparsifier for any constant epsilon. And the one thing I just want to point out is note the alpha here. This isn't an epsilon. So what we're going to get is that the cuts are approximated up to an arbitrarily good epsilon. The flows, you'll lose a log. Or here we'll lose a little worse, but we could lose a log. And that actually is kind of real. Roughly, if you don't actually use the demands, you run into something resembling a flow cut gap kind of issue, which is that you're trying to route all demands, and you get some congestion from the worst case over all of them. So we get the cuts right, but the flows, it's up to a log, but we're not going to really worry about it. OK, now here's my picture for how it works. This will be a slight lie, but not a terrible lie. Roughly, the whole construction of flow sparsifiers are kind of 2 steps, which is figure out how you'd want to do it in expanders, and then figure out how to pretend everything is a bunch of expanders. So the how to do it in expanders is pretty easy. You could actually choose one of several ways to answer it in expanders. But roughly the idea is it's easy enough to subsample expanders to get sparse graphs, but the problem is the embedding. For the embedding, we're actually just going to use electrical routing. On expanders, routing in any kind of reasonable way should work pretty well. Electrical routing is a good one. And so what you can do is you can show that more or less the competitive ratio of routing something with electrical flows depends only on how good an expander it is. And so if I just want to route on expanders, electrical flow is actually a good enough competitive algorithm. So for general graphs, we're just going to chop it up into expanders. So for general graphs, the idea is you'll show you can break your graph into a bunch of, I'm not going to say expanders. I'm saying well-connected because it's not quite expanders, but morally expanders. A bunch of well-connected clusters that contain a constant fraction of the original number of edges, of the original edges. So you show that you can cluster any graph into a bunch of well-connected components connected by fewer than a constant fraction of the remaining edges. And then on each of those, on each of the well-connected components, you're going to find sparsifiers and embeddings because they're expanders and we're good at that. And now we've removed a constant fraction of the edges. And then we're just going to repeat. So we're going to take our new graph, then divide it up again, et cetera. And that's kind of the core of the flow sparsifier construction. For the vertex reduction, roughly the idea is what we're going to do is we're going to embed not into trees, but into trees plus a little bit. So if I gave you a graph that was, you could have done it as trees plus a couple edges or trees plus a couple vertices. Let's do trees plus a couple vertices here. The idea is if I give you a graph that is an arbitrary graph on some number of things plus a bunch of trees, then you can not pay for the tree part of it. Routing on trees is really fast. And so what we're going to do is embed into graphs that look like that. They're like m over t vertices plus some trees coming out of them. And then you can actually get this with embeddings. And the claim is that you can reduce routing on one of these graphs. So the previous stuff showed this for cuts, and we're going to show you can do embeddings too. And roughly the idea is you can reduce routing on one of these graphs to routing just on the core in the middle, because you can just kind of contract out the hair at the edge, right? Like routing on paths and leaves, there's only one way to do it, and so you can just contract them out. And so putting that together, you get vertex reduction. The idea is you show that you can reduce, you embed into a distribution of core plus trees, then you collapse the trees, and that gives you your running time. OK, so that's actually the whole thing. So just to recap the whole picture, outer loop is L infinity gradient descent to minimize congestion. To do that, each iteration, you're going to use circulations to improve the congestion iteratively. So find a circulation to improve repeat. To find the circulation, you will apply a circulation projection matrix. The circulation projection you construct with an oblivious routing scheme. The oblivious routing scheme you construct recursively. To construct the oblivious routing scheme recursively, you'll show how to reduce the number of edges to something that depends on the number of vertices, and to reduce the number of vertices to something that depends on the number of edges, and repeat. And for this one, that was the flow sparsifiers. For the other one, it was distributions over things a little more complicated than trees, which lets you use a lot fewer of them and gets us our implicit representation. And putting that all together gives max flow. Multi-commodity flow is really not much change. You use the same everything. You just change the objective function and the regularization and the norms. But like use the same circulation projection, write the right thing with gradient descent, and do it. So it's really not a major change. And you don't need to redo the combinatorial stuff. You can just redo the outer loop. OK, so that's it. And if you have any questions, let me know. Thanks.